Hello everyone and welcome back to the Limit Math. We are a math tutoring nonprofit organization with the goal of making math and problem solving approachable and enjoyable to all. So in this video, we're going to be talking about the angle bisector theorem, which is a theorem in geometry that arises whenever we have a triangle and one of the angles in the triangle is going to be bisected by segment. So in this triangle ABC, we have angle A being bisected by AD, such that angle BAD and angle CAD are both equal to each other. So what does the angle bisector theorem actually say? Well, there's two parts to this theorem. The first part states that b over x, the ratio of the lengths b and x, where b is the side opposite b and x is one of the parts of BC, is equal to c over y. And the other part of this theorem states that e squared, where e is the length of the angle bisector AD, is equal to BC minus xy. So these are the two parts of the angle bisector theorem. We're going to be looking at the proofs of both of these statements, and then we'll go into some example problems to see how to apply the angle bisector theorem. Alright, so let's go ahead and take a look at how to prove this first part of the angle bisector theorem, which states that b over x is equal to c over y. And the way we're going to do this is by extending AD to a point E, such that BE is going to be parallel to AC. And I'll explain why in a minute. So let me just go ahead and set everything up. Okay, so as you can see now, we have extended AD to a point E, such that BE is parallel to AC. And the reason this is useful is that it creates some nice similar triangles. So notice that AC and BE are parallel. So since AE is a transversal of these two parallel lines, angle CAD and angle DEB are going to be alternate interior angles, which means they're equal. So this is going to be alpha. Angle DEB is going to be alpha. Since angle DEB is alpha, and since angle DAB is alpha, we know that triangle ABE is an isosceles triangle. So this side is going to equal this side, and we're going to have BE is equal to C. And the similarity comes from the fact that these two angles are vertical angles, which means that triangle ACD is similar to triangle EBD by angle-angle similarity. Right, so let's go ahead and write down our similarity ratios from this similarity. We have AC over CD is equal to EB over BD. AC we know is B, CD is X, EB is equal to C, and BD is equal to Y. So with this similarity, we have proven that B in our triangle ABC, B over X is going to be equal to C over Y. So let's go ahead and move on to the second part of the theorem, which states that E squared is equal to BC minus XY. Okay, let's go ahead and prove the next part of this theorem, which states that E squared is equal to BC minus XY. And the way we're going to do this is we're going to use a theorem in geometry known as Stewart's theorem. So if you're not sure of what Stewart's theorem states, let's say we have a triangle ABC with a CVN of length D, which divides BC into M and N. And let's say the lengths are C, B, and A. Well, Stewart's theorem tells us that MAN plus DAD is equal to BMB plus CNC. So let's go ahead and apply this directly to our triangle on the left here. So applying this to our triangle, we get that XAY plus EAE is equal to BYB plus CXC. Right, and let's go ahead and use the fact that A is equal to X plus Y and simplify things a little bit. So we get that XY times X plus Y plus E squared times X plus Y is equal to B squared times Y plus C squared times X. And our next step is going to be to isolate E squared. So we get E squared is equal to B squared Y plus C squared X minus xy times x plus y all over x plus y, right? Simplifying a little bit more, we get that E squared is equal to B squared Y plus C squared X over x plus y minus xy. And now we're going to use the statement that we proved last time. What we proved last time was that B over X is equal to C over Y in our triangle, right? So using this fact, we know that X is equal to by over c. And we also know that y is equal to cx over b. So using these two facts, let's go ahead and substitute x and y for by over c and cx over b in our denominator on the left. Doing that, we get e squared is equal to b squared y plus c squared x over by over c plus cx over b minus xy. Okay, and now let's combine, let's simplify the denominator a little bit more, and we get b squared y plus c squared x over b squared y plus c squared x over bc, right? We have just gotten it under a common denominator, minus xy. And if you notice that when we multiply by the reciprocal of this term down here, in order to divide, when we multiply by the reciprocal, bc comes on top, and on the bottom remains b squared y plus c squared x. And this term over here is exactly identical to this term, so these two cancel out. And what we're left with is bc minus xy. So we have proven that e squared is equal to bc minus xy, which is exactly what we wanted to prove. So now that we have proven both parts of the angle bisector theorem, let's go ahead and get into some examples to see how we can actually apply the angle bisector theorem in some contest problems. Okay, so let's take a look at the first example. This first example is from the 2009 AMC 10B, problem 20. We have a triangle with a right angle at B. We're given that AB is equal to 1 and BC is equal to 2. And we want to find BD. So the way we're going to do this is we're going to simply apply the first statement of our angle bisector theorem, which tells us that 1 over BD is equal to AC over DC, right? Our angle bisector theorem tells us that if BAD and DAC are equal angles, then 1 over BD is equal to AC over DC. Well, how do we know what AC is? Since ABC is a right triangle, and AB is 1 and BC is 2, by applying the Pythagorean theorem, we know that AC is going to be the square root of 1, root 1 squared plus 2 squared, which is root 5. So we know that AC is root 5. Plug that in, we get 1 over BD is equal to root 5 over DC. Well, we don't know what BD or DC are, but we know that the whole thing, BD plus DC, is equal to 2, right? So let's split BC into x and 2 minus x. So if we split up BC into x and 2 minus x, we get that 1 over x is root 5 over DC. And DC is 2 minus x. And we're trying to find x, right? Because x is equal to BD. So if we simplify this, we get that 2 minus x is equal to x root 5. Moving the x to the right, we get 2 is equal to x root 5 plus x. We can now factor out the x. X times root 5 plus 1 is equal to 2. And let's go ahead and divide by root 5 plus 1. And the last step is going to be simply to rationalize the denominator. So we multiply by root 5 minus 1 to end up with x is equal to 2 root 5 minus 2 over 4, which simplifies to root 5 minus 1 over 2, which is our final answer. Okay, so let's take a look at the second example here. This is from the 2000 AMC 12. It is a little more involved than the last example, but I highly recommend that you try it out before continuing. Okay, so here we have a 13, 14, 15 triangle. D is the midpoint of BC and E is the intersection of BC with the angle bisector of angle BAC. Okay, so we're asked to find the area of triangle ADE. The way we're going to do this is we're going to simply find the altitude from A to BC, because that altitude is the same as the altitude from A to DE, right? And once we find that, all we need to do is find DE in order to use 1/2 base times height and calculate the area of triangle ADE. So how would we find the altitude from A to BC? Well, let's say we have, let me draw it to the right to reduce the clutter over here. Well, we know that ADB and ADC are both right triangles, so let's try to look for some Pythagorean triples where the hypotenuse are 13 and 15. Well, the only Pythagorean triple that comes to mind with a hypotenuse of 13 is 5, 12, 13. So either BD must be 5 or BD must be 12. Well, if we let BD be 5 and AD be 12, then we see that DC must be 9. And we see that this arrangement works because BC equals 14, which is what we started with. So now we know that the altitude from A to BC is going to be 12. So all we need to do now is to find DE in order to use 1/2 base times height. So let's let DE equal x. And since BD equals 7 and BC, the whole BC, is equal to 14, we know that EC must be equal to 7 minus x. Right? And now we can just use the fact we're given about the angle bisector. So we know that BAE, the angle BAE, is equal to angle CAE. So based on that, we can write down from our angle bisector theorem that AB over BE is equal to AC over EC. So plugging in the values that we know, AB is equal to 13, BE is equal to 7 plus x, and this equals AC, which is 15, over EC, which is 7 minus x. So let's go ahead and cross multiply. We get 91 minus 13x is equal to 105 plus 15x. 28x is equal to 14, which gives us that x is equal to 1/2, right? So we know that ED is equal to 1/2, and the altitude is 12, so we can find the area of ADE by 1/2 base times height, which is 1/2 times 1/2 times 12, and this is equal to 3. And with that, we have finished the problem. That was the final answer to this AMC 12 problem. And at this point, we are done with the video. Thank you for watching. If you guys have any more video suggestions that you would like us to do, you can drop them in the suggestions form linked in the description. And you can also check out our website for more details in the description. And that's it for this video. Thank you for watching. See you in the next one.